starting discussion. You know? So yeah, so I was right. So I was trying to discuss what are the ways of arriving at hybrids, right? Hybrid systems. So I think, in my opinion, there are three ways, and they're not equivalent. So the first way is, as I just mentioned, that we have a full quantum theory and we make a semi-classical approximation on 1 degree of freedom, which will become quantum, which will become classical. The second approach would be to start with a fully classical theory and quantize only 1 degree of freedom. And the third approach is sort of having a quantum system coupled to some reservoir, larger system, which was supposed to be inducing some decoherence and therefore decreasing, sort of becoming more classical-like. So where the first two approaches are sort of well understood, the second one, I personally have a little bit of a problem, because the coupling of a quantum system to some reservoir gives not a classical system, but rather open classical system, not a closed quantum system, not a closed classical system, but open classical system. So my question is, just to start this conversation, is are there other approaches that perhaps one could explore, you know, and are we missing something? Am I missing something? Or are there other approaches? Can we come up with some other approaches? I was myself personally was thinking along the line, since we have here many chemists, for whom running big simulations is you know, it's a piece of cake. And I was particularly thinking, is there a way, and also along the Koopmanism as developed by Igor, who just spoke, is there a way, for example, to see, to be able to see emergence of some kind of hybrids by looking at like large simulations of many quantum systems, something like this? So some other way, like just numeric, not even maybe analytical and mathematical, but just some other ways of seeing this. And of course, this is all motivated by the question of finding sort of maybe what kind of experimental scenarios one could test. One could argue for existence of hybrids, and of course there'll be some by Professor Els that will be talked tomorrow of interest. So, but again, let's just start discussing.
Can we just talk freely?
Yeah, exactly. Yeah.
So I apologize first of all if I'm not an expert in all of the techniques you mentioned, but would you consider the approach where you take a classical system with say a commutative algebra of observables and you try to embed it in a non-abelian, quantum system that is based on a non-abelian operator algebra, while maintaining some sort of consistency relations between the various levels, a separate approach, or some example of one of the approaches you mentioned?
I would, could you a little bit more elaborate?
So I'm thinking that if you have a classical system and then you embed, you have a procedure that you can embed the classical states into states of a quantum system, sort of injectively in a one-to-one manner, and also you can embed observables of the classical system into observables of the quantum system, and you can do this in a way that is compatible with the dynamics. Would that be another example of, it's not really doing quantization per se, but it's more like representing or encoding a classical system through a quantum system?
In my opinion, yes, it sounds like definitely. And I presume you're going to talk about this, right? In your
some aspects of it.
Yes, the presentation. Yeah, so this definitely would count as another way of sort of running everything on a quantum computer, but shall we say, like in the popular vulgar terms, right? Like basically, you translate everything to the big quantum simulation, to big quantum
So am I correct in saying that in that approach you would postulate the form of the Hamiltonian?
Of which, of the classical or the quantum?
Of the hybrid system.
Like
how would you let, I mean, I don't know, I don't know much about this approach, so I'm just asking to learn more. I suppose at some point you will have an interaction potential of some kind.
I would think of it more sort of in the sort of framework that, you know, this operator theoretic framework that Igor discussed. Namely, we have a classical system. It doesn't even have to be Hamiltonian system. It can be some type of flow on a manifold, and you specify a space of variables of the classical system. So you have some notion of Koopman operator, and the Koopman, sort of the group of operators, it has a generator. It doesn't have to be a Hamiltonian, or it doesn't have to come out of, let's say, Hamilton's equations of motion per se, but it is an operator, and then that can act on functions. And then the sort of the approach would be that you want to create a mapping that, you know, can take this operator and map it into the Hamiltonian of a quantum system that operates in some potentially different space, without asking necessarily sort of details of the necessarily sort of the details of the implementation of the quantum system, meaning that you just want to have a mapping that is consistent in the sense of sort of maybe, you know, preserving you can consistently represent the evolution of classical observables under the Koopman operator as expectation values of quantum mechanical observables under that mapping that you created.
Okay, yeah. So it's more like dynamical mappings rather than solving infinitesimal equations of motion. Yeah, thank you.
Maybe let me make just a remark there, because that's something that, for example, started. If you look at Mackey's book on, I think, mathematical introduction to quantum mechanics, he makes basically Dimitri's point. I mean, if you go very carefully through that, it becomes clear that the idea of observables themselves being operators is just for example, for position observables, it's just a mathematical formulation where you go from some function of position to its expansion into the eigenfunctions of the associated operator. And then the understanding of the probability aspect becomes very classical. The momentum is different, but if you go to momentum representation, it is actually the same again. So I don't think that Mackey discusses that, but it's precisely the same. And the connection between the two is just through the Fourier transform, right? So, so there is a way in which, you know, Born interpretation aside, and I know I'm touching a very hot a very hot aspect, but in some sense, even with Mackey's book, you see that the Born interpretation can be, you know, taken in a Koopman, what we consider a Koopman context today, absolutely classically, just a different mathematical formalism. It's just densities on some space, right?
Absolutely.
And yet the non-commutativity of the quantum mechanical algebra of observables is usually held up as, certainly even today, as the distinction between classical and quantum mechanics. And yet the Poisson bracket is used to construct operators which don't commute with the observables. The Hamiltonian, obviously, is the first example, gives you the Liouvillean operator. So the way I would see Dimitrios's construction, so to speak, would be to say that would be to introduce the GNS construction, the Gelfand-Naimark-Siegel construction, which gives you then a Hilbert space. And to do that very much in terms of Whiteman's axioms, and modifying that to accommodate the fact that you're talking about what in the math is I think usually called a random field as opposed to a quantum field. And in that sort of construction, now the classical mechanics, by allowing those non-commutative that non-commutative algebra which you can construct using the Poisson algebra, the Poisson bracket, it then becomes a quantum mechanical object. It is a Hilbert space. You can then construct a Hilbert space once you've introduced a state that that gives you measurement results for those extra operators. So you need to the state that we have been working with for a classical object has merely been a state over just the commutative algebra, the central algebra. Once you introduce the additional operators, so in effect you have, as well as Q, you have partially Q, and as well as P, you have partially P. So you have all of those operators. Now your state has to be a state over that enlarged algebra. So to do that, you simply have to postulate it, I think. And the way what you postulate determines what the physical model will look like. So that for the simple harmonic oscillator, you start off with the Gibbs state over over Q and P. To extend that, which is a Gaussian state over Q and P, to extend that to partially Q and partially P, the obvious choice is to just make it Gaussian over the partially Q and partially P as well. And that's, so to speak, just a starting point. If you're going to do something else, the thing is you're now talking about representations of the Weil-Heisenberg algebra, Weil-Heisenberg group. And so there's only one thing you can do. There's only one, the representations are unique up to the choice of the constant variable, up to a constant. So now with that kind of construction, you no longer talk about classical systems and quantum systems, but there is a distinction, there are distinctions to be made between classical and quantum. And to me, the distinction is that the Hamiltonian that generates evolution is positive definite, whereas the Liouvillean operator that you generate using the Poisson bracket is not positive definite. And that's a huge difference. It just bears to all of the analytic properties of quantum mechanics you no longer have. But you really can make a connection with something out of signal analysis, and so much can be made of thinking in signal analytic terms about this, I think. The Hilbert transform is very much of the same type. And one speaks of the analytic signal in quantum mechanics, in signal analysis. And as a result of that, by taking that analogy, I very much think that quantum mechanics can be just regarded as an analytic form of classical mechanics, because you have specifically taken all the positive, you're only going to talk about positive frequencies. Negative frequencies, you're just going to transform away the negative frequencies. Once you've done that, then you have a very analytic sort of structure. Okay, sorry. Talk.
Very good. So Jonathan, please, could you?
Beg your pardon?
No.
Oh.
I feel like the answer to your question depends a lot on what the objective is. And I think it's worthwhile going back to the discussion that Diyoshi and Stephen Fulling were having in terms of what's the motivation? If your motivation is that you believe that fundamentally there's a classical and quantum system, and that one system is fundamentally classical, then I think there's almost no choice. There's effectively a generalization of the equations that Diyoshi showed, which that's the only choice you have. That's the only valid dynamics, which is completely positive and trace preserving. If you, on the other hand, believe the world is fundamentally quantum, all of it, then I think there you're pretty much doing, you know, what you said, Dennis, which is, for example, imagining that the system that you want to classicalize is interacting with a heat bath, or you know, there's various ways you can do it, or taking coherent states or something like that. This, you know, and there you don't care so much that your equations of motion are not completely positive, because it's just meant to be an approximation. It's not a fundamental theory. It's a bit unclear to me where these other formal methods fit, because they seem to be more about the mathematics. And so for even the Koopmanian approach, you know, I don't know, you know, I need to go to the probability density to see if the classical system stays classical and the quantum system stays quantum, and I have to go back to the, you know, I have to go back to the density to see if it's completely positive trace preserving. So for me, it feels like those formal methods may get you some insights, and they may be beautiful, but unless they are shown to be equivalent to these other two approaches, it's unclear to me, you know, for their status then has to be put in a bit of a sidebar, for me at least, because you just don't know if they correspond either to completely positive trace preserving linear dynamics, which you have to be if it's a fundamental theory, or whether they correspond to some actual notion of taking a classical limit when we have two interacting quantum systems, if you believe that fundamentally everything is quantum and that this is just an approximation to what we see around us.
Just a comment on that regard. You may well believe that everything is quantum, but for instance, in dealing with the gravitational degrees of freedom, the fact is we don't have a completely workable quantum theory of gravity. So even though you may have the deep belief that fundamentally and underneath it all, there must be some quantum theory of gravity, it's not the case that you can simply take that quantum theory of gravity and a quantum theory of matter and just proceed to, you know, treat classically, you know, derive the classical approximation, the approximation in which one of these sectors is classical. So it's not. I mean, even though in principle these are the two paths, in practice we face a serious problem.
No, I completely agree, but I just mean that in terms of choosing what methods to use, we need to choose a method which corresponds. If you believe that fundamentally gravity is quantum, for example, but we just don't know what it is, then, and you want to study this so-called semi-classical limit, depending on what you're, then you need to choose a method which corresponds to having two fully quantum theories and taking the classical limit of one of those things.
Sorry, Igor, go ahead.
You have a brief comment? I just like to offer a perspective from, and I'm again sorry that I didn't get to show you the Schrödinger equation part, because it has perhaps an interesting point with respect to this current discussion. You know, in the view that I presented, if you're below the oscillation, if you're within the oscillation frequency of the observational field, then you can call it quantum. And if you're quite a bit above, you can call it classical. Think of waves on a surface of a pool, and you're looking through to see down an object, right? If the object is very large compared with a typical wave wavelength, then you're going to see the object very clearly. If the object is very, very tiny, you're going to see it moving, despite the fact, even if it's sitting still, you're going to see it moving. So what is interesting to me from this perspective is, you know, there is a clear cutoff, but also a clear idea on where we would need to do experiments, which is precisely that transition layer between, you know, where the wavelength of the observation field is comparable to the size of the particles. And you know, if we had experiments that we all know we don't, right? By, I think, a very serious set of orders of magnitude, that would actually clarify some of these issues. The part that I want to point out is that things like gravity terms in the Schrödinger equation that actually disappear if you take that point of view are the ones that have very low C over V, which is the index of refraction, right, in the formulas that I gave. And so you can almost pinpoint it. There is, I don't know if people have read the Paralagos's papers, where he introduces a term that goes between classical and quantum, parameterized by some parameter, let's call it lambda. It's straddling of the surface. It seems to me that is governed by the inertial part of the motion. How curved are the trajectories in space? Again, if anybody is, wants to look in some detail on what I've shown, please look at the slides and you will see those terms. They come out of mathematics as when you reduce everything I've said to Schrödinger.
Igor?
Yes.
Igor?
Yes.
You rely on mathematics. Do you have any guess at the scale that separates quantum from classical? Is that related to the Planck scale, or which means that you forget about the popular tabletop experiments on tabletop versions of quantum gravity or semi-classical gravity? So where is your border between?
Professor Diyoshi, first to say I'm very honored to be in the same room with you. That's my first statement. That's my first statement. The second is it is pleasant that you have a question on this. I was hoping that you might ask something. Yes, so it is precisely the Planck, because if you take a look at my field Y, it was related to action divided by h bar. And so the oscillations were really governed. I mean, the wavelength of oscillations were really governed by h bar. So it's pretty consistent with that point of view that I just made, which is that, classical is something that, in the theory, actually, very, very nicely, classical is something that's just on a much larger scale. And quantum is something that is on smaller scale. But the theory, and this is a postulate, separates two realities. It is closer to, I think, what I hope you're quoting correctly, but your ideas and Roger Penrose's ideas, which is that gravity is gravity and quantum is quantum. And this is a proposal that says, indeed, they're different. It produces an observational field, and from that perspective, you can really separate them. There is a velocity field, there is the gravity-driven velocity field. There is nothing like Bohm. There is no issue with the Bell inequality because there are no hidden variables. There is an observational field. So it is consistent from that perspective, and it gives a proposal on how to really cross the boundaries. Thank you again.
Thank you.
A different aspect in which we think of everything as being classical rather than quantum is that all our experimental data, the stuff that's stored on as many, many exabytes of data now, is essentially classical. And that data is everything we have from which we say, and here is this quantum stuff. So somehow we've taken all that classical information and we have inferred from that by methods which I characterize as signal analysis. Something else. What we're saying is quantum. And yet, if we just say, well, classical and quantum are exactly the same, it's just that classical has to have added to it the non-commutative algebra that can be constructed using the Poisson bracket, then the tools of signal analysis are perfectly capable of introduce, precisely because the Wigner function is commonly used in signal analysis, of course. You construct something in Hilbert space from the classical data, and then you talk about the observables on that, which includes non-commutativity and must include non-commutativity because there are some probability distributions which cannot be constructed out, from which you can't construct joint probability distributions. And that's something that is entirely a classical aspect of probability theory. It's been known since the mid-19th century, Boole's conditions, which is what gives you Bell inequalities. But Bell inequalities are not a problem at all for signal analysis and indeed for classical mechanics extended by this making it into a non-commutative algebra. So that's a different way of saying, and indeed the whole thing about quantum gravity, the introduction of gravity and worries about whether it's quantum or not, you have to infer that it's quantum or not from the experimental data you have, which is all classical. I mean, obviously that's a very Copenhagenish way to think about it and not adopting all of that metaphysics. But nonetheless, if you say we're deducing from classical data what we want to say about the world, what's the best way to talk about that? How can we best compress it? And indeed, there's already a huge amount of compression has gone into those exabytes of data, because any event that you store information about is already you start off with a signal that just suddenly goes bang, and you say an event happened then. And instead of storing 1 byte per picosecond to say what the signal level is, you just store 8 bytes every time an event happens. It's huge compression that you've just done. So it's already compression, and indeed that's not described quantum mechanically because we're just using a piece of hardware that is designed by an electronics engineer, and he stores away into computer memory something which then the quantum mechanic comes along and uses. Okay, enough.
No, Peter, thanks. Actually, I really much like what you say. In fact, there'll be a little bit about this. Share your point of view in our mine and Cesare's talk.
Oh, good.
I will make some comments on this. Yes, thanks. I appreciate it. Actually, another perspective actually on this quantum classical interaction is actually by late Freeman Dyson. He actually personally he would say that, there's even a YouTube interview with him that one can find and point to, that, for example, he said that the quantum and classical world, they don't interact at all, they just coexist. Because he actually had an opinion that, for example, quantum world is about future, right? It's a measurements that have not yet been realized, while classical physics is about past, the measurements that have been realized. So we have actually right, there is quite a multitude of opinions, which is good, right? Like that's nice for research, right? So he was against. He said he's very much against saying that the world is fundamentally quantum mechanical, and we have to infer kind of existence of classical theories from that. So he said like these two worlds coexist, basically.
I mean, Freeman, of course, is a brilliant physicist, but I think on this he's very wrong. I mean, and there are experiments that people have proposed to test the quantum nature of gravity. So coming from quantum information theory, and Peter said, I agree with Peter that fundamentally the data we use we treat classically, but a Bell inequality, we explain it by well, there we may go off into a thing, but when we violate a Bell inequality, what we assume is that as far as we know, the theory which explains that is quantum mechanics. And likewise with gravity, the theories that the experiments which have been proposed are, if gravity is quantum, then it can create entanglement and over large distances, and if it's not, then it can't. So by testing whether you can entangle two masses, you can test whether gravity is quantum or not. So, I think we now, the more modern view is that you can in fact test the quantum nature of gravity. So it's not just something that exists independently.
I had a small.
Sorry.
Yeah, go ahead. Yes, yeah, Benito.
Sorry, I had a small comment about this idea of Dyson, which I found, which I agree with Oppenheimer. I think it's completely unnatural because, first of all, we don't really know when measurements happen or where in space-time they occur. We only know this in quantum mechanics, where we have a distinguished Newtonian notion of time, and we can really say measurements have not happened or measurements have occurred. But let's say you wanted to do a measurement theory for quantum field theory, then you don't really know. You say something was measured, but you don't know where in space-time such a measurement took place. So I really think that this is not a correct point of view. That this is not to say that I'm completely against the idea that classicality and quantumness can coexist at a fundamental level. I'm just saying that this picture sounds completely wrong to me, as it is I mean, as much as I respect Dyson, I think he's a fantastic physicist and mathematician. I think this is not the right viewpoint. And for me, I always think of classicality in terms of something more having to do with states than observables. So I tend to think of something classical as something that is extremely coherent, that there are no, so something that is very far away from having any superpositions and being very coherent. And I often think of gravity in the classical way that we describe it as something that could be really a coherent state of quantum gravity. That it's just so hard to find any hint of entanglement in the gravitational field. But this is just, of course, I'm not a specialist, and I'm also not so well informed in all the philosophical advancements in the direction of whether the definition of quantum in itself. But to me, it has to do with measurements indeed as well, and classicality has to do with coherence. And but I guess that's what I wanted to say.
I also wanted to mention something, since we have some people from chemistry coming from physical chemistry, that, for example, there's let's take this traditional interpretation of the Bell's inequality that we need quantum physics to explain, which actually I agree. And of course, the key part is that like certain correlations that we call entanglement that has been mentioned. So it's interesting that in quantum chemistry for many decades, like from 60s, right, it has been known that many body systems could be represented by classical density. There's one-to-one correspondence between the fully multi-body multi-body wave functions with the density defined on a three-dimensional space. So one-to-one correspondence. It's called density functional theory, and this is really fascinating. And I only saw very few work like trying to see entanglement in these type of terms, in this type of language, where you just work with the density, probability density, classical positive probability density on the configuration space. Fine. So as I said, this idea of like world being fully quantum or not fully quantum is just, I think it's a still open question. It's just this way. By the way, I put forth the Dyson idea. It's not because I agree with it, but it's just because to discuss, to provoke discussion. Obviously, it's and Dyson is a pretty. Yeah, I had a chance with him to meet in person, just in Princeton. So it was pretty historical, personal meeting. Yeah. So also in the way, it's also very interesting to remember that in many experiments, especially like again, if you're trying to keep bugging our physical chemist community, right, we can actually do quite a bit of modeling using like classical trajectories, some classical, many experimental factors, quite successfully. With sometimes you need to add extra feature like tunneling, which we would just add by introducing some kind of some additional feature that is not in the dynamical trajectories in the Newton's equations of motions. So this fact itself, I think in itself also deserves maybe a bit of a philosophical consideration, not just a kind of okay, for practical reason it works. So that's what it is. But you know, like, but it actually works so often that one probably should start thinking about this. Yes, Professor Giosi.
Yeah, I have a practical question to the part of the audience who are not exactly in foundations are interested. So if we know about the popular quantum classical Liouville equation, that it may violate the positivity of the state. It can happen dynamically due to the equation, but it can easily happen right at the beginning when you take a partial Wigner projection of the fully quantized state. Because the Wigner function, the common Wigner function, may have negative parts. So my question, how and whether are the quantum chemists are sure that they never run into the difficulties of positivity non-conserving when they are applying their quantum classical Liouville equation. So whether do they have any experience, any say bad experience that their numeric algorithm would run into instabilities just because of this difficulty of the basic equation, that it may lose its sense under some circumstances. So what do we know about this?
Excellent question. So could real chemists comment on this?
There are no chemists in the room, and therefore
No. For example, Aurelia is here. Aurelia is still with us. So
Aurelia, yes.
Yes, no, it's not true. Aurelia, do you want to comment on this? Because actually she has done herself quite important work.
You classify myself as a chemist?
For the purpose of this discussion. I said physical chemist, right? I keep referring to physical.
Okay, so then I hope there are really no chemists here, because otherwise, yeah, I mean, I cannot really comment on. So you want an experiment or something like in the physical world that will tell you you don't want run into problem of positivity, right?
Yeah.
Maybe even just a comparison, you know, with the realistic simulation from the quantum.
You see, well, maybe, I mean, that might not answer your questions, but I can tell you that if it's a Redfield master equation that does not necessarily conserve positivity of the density matrix, so then you might not like it in the sense that it's not physical, still gives you, well, some physical answer in wave behavior dynamics. So sometimes, so the Redfield master equation compared to the Lindblad master equation will not have the circular approximation. You will have coupling between coherence and population in very short. And sometimes it is preferred to model systems like, well, the one I have in mind as population transfer in light harvesting system. So in per se, the equation does not always maintain positivity, but it is still useful. I'm not sure this really addressed the problem. I mean, the question of how you would really test this issue of positivity. It's the only thing that comes to mind now.
If I also may add to Professor Diaz's comment that in my experience when I was talking with the also real chemist a while ago, so, on the same question, and he replied to me, I will not tell his name, said to me, you know, our model has 20 parameters. It does not preserve positivity. We can always make it preserve positivity by tweaking those 20 parameters. So, so there is this point of view as well. I saw that Jared had a question or comment. So maybe let Jared.
Well, at the risk of beating a dead horse, coming back to this idea of whether or not kind of, you know, you can have intrinsically classical systems coexisting with quantum ones. I think like the problem and the reason why I think most people kind of feel that's a bit aberrant is that there's no natural way then of deciding what is the domain of intrinsically classical systems. When does that actually apply? Whereas if you think everything is fundamentally quantum, we know how it is that in some limit you can get behavior that appears classical. So I think on some level, right, this may be one of the idiosyncrasies of Dyson, that on some level I think he wanted the world to look incomprehensible. Yeah, that's all.
One aspect of the Bell inequalities that I think is, well, I'm pretty sure is not very well known outside of the sort of technical literature, is something that was very much discussed in the 1980s. It comes out of a paper by Arthur Fine in 81, 82, which is, then there's a very mathematical paper that says, if your algebra of observables is commutative, then this particular Bell inequality will not go, you can't exceed 2. If your algebra of observables is a non-commutative algebra, then there are states for which you will not exceed 2 root 2. So that is the, I've forgotten the name of that, oh, Sarelson, the Sarelson limit, so to speak. And then 4 is the absolute mathematical maximum possible, which can be achieved using the right quantum computation sort of stuff, fancy going into, I'll stop because I can't put it well. But what this says is that the, if you take that view, instead of worrying about locality, about reality and such like, if you just focus on what the observables are, if the observables are commutative, there's a purely commutative set, then you can't exceed then you can't exceed 2. If the algebra of observables is not commutative, it's non-commutative, then you can exceed 2 and get as far as 2 root 2. If you take the view that it's purely about those observables, and really the proof is it's half a page. It's in many ways much simpler than the sort of discussions you see from Bell and in all the subsequent and much of the subsequent literature, because it does not involve reality or locality whatsoever. It's purely in this literature about non-commutativity. So if you see the violation of Bell inequalities, that does not prove that something is classical or quantum. It just proves whether or not the algebra of observables that you would need to describe the process that you have used to get those numbers. You have to use non-commutative algebra to describe that system of algorithms, that system of signal analysis that has resulted in those numbers. Because you started with long lists of times at which you've observed events, and out of that you've come to a number which ostensibly, well, is bigger than 2. And if you don't allow yourself to use non-commutativity, then you can't get to that number. But if you do allow yourself to, which signal analysis does let itself do, but classical mechanics is made into a straw man by saying you may not use non-commutativity in classical mechanics. So that sort of says, let's not worry about locality, about reality. Let's simply worry about whether it's natural or not for a classical physicist to use signal analysis, all the mathematics of signal analysis, essentially. End of story.
So Peter, actually, I also want to testify to the kind of methodological power of this derivation from 80s, how like non-commutativity and violation of balance inequalities. I actually tried to teach this in a class, quantum
All
mechanics,
right.
in the graduate class. It's really goes really well after uncertainty principle. It's so easy. Actually, so easy to do this. But actually, I disagree with you on that part, on the second part.
Right.
Because for me, if the algebra does not commute, the thing is that the algebra and states are not independent. What happens is that, as I will talk tomorrow, the non-computative algebra gets entangled. If you want to represent dynamics in non-computative variables, it gets translated into a Schrodinger equation, unlike the Koopman von Neumann equation or legal equation. And that's in terms means that your non-computativity, which started as purely algebra of observable, gets transferred or leak into the states. And in that regard, the presence of the non-computativity immediately is that, for me personally at least, this is my personal point of view, is the definition of quantums. If you need non-computative algebra to describe these things, that's actually quantum mechanics, and therefore, in this way you reconcile two views of Bell's inequality. That old views like from 80s that it's non-computativity, and the more recent view, like kind of Bell's original view, basically, right? That it's sort of about correlations, non-local correlations.
Right. And from a quantum field theoretic point of view, I see the relationship between locality and non-commutativity coming purely out of macrocausality. That it's only when observables are time separated, the time-like separated, that you have non-commutativity. And so locality is closely associated with non-commutativity purely by that relationship through the macrocausality. And that's the field theoretic relationship that I would see as being, but this is to split hairs in some way. I agree that if you say anything that's non-commutative is quantum, anything which is commutative is classical, then there is such a thing as quantum and classical. But it seems to me that that distinction is very much eroded if you say, well, actually, we're starting with classical experimental data, and from that we are constructing this description of the world in which we're using non-commutativity. So at what point did you introduce some sort of analysis of this original data, which has forced you to say we must use non-commutativity? So that seems to me to be a different way of asking the question than just to say, oh, everything's classical, everything's quantum, and instead to say, well, actually, everything is just something in the middle, because and the trite sort of thing I've been saying over the last 6 months, I guess, is that instead of adding hidden variables to quantum mechanics, we should be thinking in terms of adding hidden observables. I can't even get it right. Hidden observables into classical mechanics, and these hidden observables have been there all along because of the Poisson bracket, and because we use the Liouvillean operator, which doesn't commute with position. So we're using it all the time already. So it's to say they're hidden is ridiculous, because they've not been hidden forever. They've been in plain view since Dirac said, "Hey, let's talk about the Poisson bracket."
I agree with that point of view. I mean, I don't know if it came through, but what I spoke about is actually a proposal in that direction.
Yes, I mean, I actually, well, I'll say now that because it seems too disruptive in a way, what you're doing sort of reminds me of the Whiteman axioms, because you're using something that's quite similar to a test function, as basically smearing across a world tube, and that's just a test function. And but on the other hand, Whiteman's axiomatic construction, which is very much from what Mackey was doing. I mean, I think Mackey is very much the motivation for what Whiteman introduced
Yep.
And then, of course, you have the Haag-Kastler axioms coming in later, even more, I think, motivated by Mackey's sort of ideas. But if you do that, the axiomatic construction is quite different from what you have in, well, in any classical mechanics, really. I mean, the Lagrangian is irrelevant. You simply have to, give an algebra of observables and a state, and everything is there, so long as the state and the observables have Lorentz invariance in the various ways it needs to have. So I kind of was seeing what you were doing and thinking to myself, well, but Whiteman kind of does that cleaner, with apologies, but you know, and so,
No,
but of course the thing with Whiteman is that Whiteman has no models. It only has free field models, and that's been the complaint about that. So something has to change for that to be useful. And in practice, no one has really said, well, what other axiomatic system as beautiful as that, which, you know, admit it has that mark against it. It's beautiful, but useless as it is. So what would we want instead? What kind of axiomatic system? What has to change? Or does it just have to be replaced wholesale, which perhaps your approach might work, where the Whiteman system can't be changed in any way that will make it work.
We shall see.
Yeah. A lot of work, whatever's going to be done, it's going to take a lot of work.
Yeah. No, it's interesting, that progression of thought, right, from Mackey to Whiteman. I mean, there's been, I think what you pointed out, even in Feynman, it's pretty much implicit, right, that you get first order dynamics out of things, and that the notion of e to the is coming from somewhere. It's an additional aspect, right? It's coming from somewhere, and to a certain extent, the path integral formulation was incredibly successful in computing, and never, you know, either Dirac or Feynman never really explained where it's come from. What was interesting to me is that, you know, if you make a density assumption, at least mathematically, it's very clear where it's coming from, and it gives you the formalism back. That is interesting, but I agree that line of thought. I mean, even the recent work by Peter Holland at Oxford, I don't know if anybody has read. There is a Lagrangian approach to quantum mechanics in Foundations of Physics, and if you look at his solution for the wave function, it's an integral. It's basically a weighted Koopman operator, weighted composition operator of exactly the kind of presented just for the Schrödinger, right? Not for a full relativistic context.
Right.
And the fascinating thing to me is that if you just differentiate that integral that he derived, it's a first order equation in space and time. It is not second. Now you can take a second derivative and you will get Schrödinger, but it's a first order equation. It's just like what Dirac sought in electron. And the equation that I presented obviously is first order. You can get Schrödinger out of it if you just take another spatial derivative with, with just a little bit of mathematics. So,
right.
It's tightly connected to that whole line of ideas that, as you pointed out, and I'm also aware of it, goes from Mackey. Yeah.
So I guess my response to that is that the first order differential equation thing has to come out of, I mean, as soon as you have symmetries, so you have a, then you have generators. If you have translation invariance, time-like translation invariance, then there is a generator of that translation invariance. And so, yes, there will be a first order differential equation.
Yep.
And so I've been working always in a formalism in which I purely work in 3+1 dimensions. I know it's wildly over idealized, but that's what I do, so to speak. And indeed, my whole motivation is I don't like renormalization. So this already puts me in the crazy camp, of course. But as a consequence, your Lagrangians are just not acceptable from that point of view in a field theory context, whether random fields or quantum fields, because you are taking powers of a distribution. And you can't do that without introducing all sorts of fancy mathematics. If you're going to do that, there's an approach called Colombo generalized functions that, well, it's very nasty mathematics. On the other hand, if you work with Whiteman's kind of starting point, which I see as just being an index set of observables. And what the index set is irrelevant in some ways, except of course it's everything. Because if you take the index set to be points in space-time, then you get one theory. If you take the index set to be integers, then you get a different theory. And the relationships between those observables is determined entirely by the state. And the GNS construction then gives you a representation of that algebra. So you really want to work with a mathematically well-defined system. The way to do that is to work with what you are using, test functions, the density of functions, because those can be taken to be smooth, even though the thing you're measuring, the quantum field, is not smooth at all. It's not even continuous. It's a distribution. The quantum field is a distribution. And so you don't want to work with that. You want to work with the way that you've measured it. So instead of talking about what you're measuring, you talk about what measurements you are performing, and very much looking at how you're coordinatizing your measurements, instead of talking about and about what the measurement results are, because you're always looking at smooth things. You're never looking at the field at a point. You're always looking at the field in a micron size region of space-time. So that the test functions, and indeed in signal analysis, there's a word for this, window functions, which is exactly the concept that's being used in quantum field theory. And so you're always looking at smooth things, and you work with the test functions. So you're working in the dual space of the thing you're actually looking at. It's as if you're, I'm still trying to get out of this, but I do talk about Plato's cave. You don't know what's outside the cave. You do know what the shadows are. You know what direction you're looking in, and you look at the shadows and you move around and you see how your shadows interact with their shadows and such like, and you progressively get more and more data, and eventually you can say, oh, I've got a tomography of what's outside, but not in any clear sort of way necessarily, but you just work with, you're always working with what you're looking, with how you're looking, rather with, and what the results of that looking are, rather than saying, I am looking at fundamental reality. You just say, well, actually, I'm looking at what I see. Okay, end of story.
Okay, any more comments?
Sorry.
No. Any more comments?
Actually, yeah, if I may, can you hear me?
Yes, you can.
Yes.
Already on the move, but it's very relevant to this discussion is actually in relativity, and I think Andre, who is on this call as well, that actually classical relativistic theory is plagued with lots of inconsistencies. For example, there is no many-body classical relativistic physics. Just that doesn't exist in a normal way. The same way there's this problem of self-interactions. So I was also wondering what kind of implication does it have to our discussion of quantum classical hybrids and more, maybe even more fundamental questions, like maybe does it, yes, what were the thoughts? I was wondering.
Anybody wants to say something?
Could you repeat what you said, perhaps in a slightly different way, might help as well. But by the end, I've lost track of what I thought might be the focus of the question.
Dennis, can you repeat your question?
Yes, so I apologize if connection was fluctuating. So the key is that what does it, the fact that classical relativistic physics is plagued with many inconsistencies. For example, like self-interaction, radiation, charged particle has to self-interact, and also that there is no many-body classical relativistic physics. What does this sort of imply for our discussion? Does it have any consequence for our discussions? What's the status of the research in this sort of direction?
Well, there are at least non-interacting classical random fields. You can construct basically in the same sort of ways as the Whiteman axioms construct quantum fields, in which you can just discuss the.
My question about classical particles.
Right. No,
right.
I was
many body.
Right. So, but nonetheless, does that not mean that we might perhaps want to or need to, and indeed, electromagnetic field is a field, and it's when you add noise that things get complicated.
May I add something trivial? So I was actually thinking the same thing to ask, that the whole discussion of quantum and classical thing that we are doing, we basically are talking always in the non-relativistic regime. And in the relativistic regime, there are two things. So if we have a lot of classical particles, and if they have a substantial amount of mass, then you have to use general theory of relativity, because the gravitational interaction will actually take over after some time. But when you have very small particles and they are in the relativistic regime, you cannot get rid of antiparticles, because the very idea of quantum field theory is if you have microscopic particles and they're at very high velocity, then of course they will give birth to this antiparticles and particles whole thing. And there is another level of chaos going at in the quantum field theoretic regime. So so basically, when we are talking about this Koopman Hilbert space thing about classical mechanics, we are always in the non-relativistic regime, and we have to be at the non-relativistic regime, because the moment we go to relativistic regime, then general theory of relativity comes about. Maybe there might be some intermediate theory for classical particle. I was thinking, like, is it possible we can use this Koopman von Neumann wave function approach, and maybe we have some relativistic Liouville equation and we can do some stuff about it. That's all my weird comment and broken stuff. That's it. I hope it makes some sense.
I also want to add something. So there was lots of discussion today about lots of concerns about positivity preservation, but another concern is about polarity preservation. So definition of poor states in case of classical and quantum mechanics, and if we believe that poor state should be converted to poor state is another concern about joint quantum classical dynamics. There is a good reason to believe that poor states in classical mechanics corresponds to point particles, and if we consider any kind of joint quantum classical dynamics, it looks like we always will get mixed states in whenever definition of mixed states we will take. So it looks like we always will have some sort of approximated dynamics. So it's some addendum to an arguments, but just mixed quantum classical system is just a numerical approximation. However, I'm not sure, so can anybody comment how can we define pure state in the case of gravitational fields? Is there some ideas what we can consider as classical analog of pure states for gravitational field?
Can I try to answer?
Please.
Yeah.
Yes.
If I look at the issue of a pure state in classical physics, my approach, my belief, my published belief is that it is not about whether the particle is a point particle or an extended particle. It is about its degree of freedom or degrees of freedom. So pure state in classical Liouville theory means that the density over the phase space is a delta function. So the phase space coordinate is well-defined something. So that's the pure state. And commenting on the other part of your remark, what the status is of hybrid dynamics. You said that it must always be an approximation. Well, if you start from fully quantized theories, then of course, if part of a composite system is considered classically, then it is an approximation. It happens in chemistry and elsewhere. On the other hand, in foundations, however, we are not sure that there is any genuine, true classical system on Earth or in space or in the universe. But since gravity has not been proved to be quantum so far, this is the main motivation that mainly on mathematical grounds, we are looking for a consistent hybrid theory of classical and quantum systems. So this is a mathematical challenge, and my main motivation is just the missing theory of a fully quantized universe, including gravity. And as a matter of fact, if you construct such a hybrid dynamics, it is not an approximation of anything. It is thought to be an autonomous, independent theory for something which may not exist in reality. If the other day you construct a plausible, consistent quantum gravity, which completes our quantum understanding of the universe, then a mathematical proposal for a quantum classical joint system makes no sense anymore in the foundational context. But as long as we don't know whether gravity is classical or quantum, it is an open issue. If you are able to construct a consistent, not an efficient theory, but a consistent theory for something which is partly classical, partly quantum. That's my position.
Could you
I,
expand
Thank
on
you.
what you mean by consistent?
Sorry, can you say it again?
So I got curious about what would your criteria be. Sorry, my internet might be quite bad. I was wondering about what your criteria are for saying that a theory would be consistent.
Yeah.
So if I would give you a theory, how would you judge whether it is the one?
Yes, you are right. It is a delicate question what the conditions are, the criteria are. If the theory contains a density matrix or a wave function or a hybrid density, the criterion, the main criterion is that you must be able to apply the statistical interpretation to it, unless you propose a fully new and independent of von Neumann's interpretation for your hybrid density. So the main criterion is that you must be able to retain the statistical interpretation for the hybrid density, which means the conservative probabilistic interpretation for the phase space sector of the density and the von Neumann interpretation for the quantum. So that's the probably it is the main criterion.
So maybe I can add something to that. In the old paper by Boucher and Traschen, in the very first pages, there is a list of desired properties that a hybrid quantum classical theory should have.
Yeah.
And of course, positivity is one of those. There are also transformation properties, which I think also are important. So I would address Marek also to that paper, because it's quite an exhaustive list.
That's something I was looking for. Could you maybe type the names into
Yeah,
chat?
sure.
Because I don't
So
know
let's see if I can post that paper on the chat
That
here.
would be wonderful. Thank you.
In the meantime, please, you keep discussing.
So if I understand correctly, the positivity issue is something that one has to discuss if you're aiming for a hybrid, right? So
Yeah.
so merging the standard model with GR, right?
If you lose positivity, you lose the statistical interpretation, both the classical one and von Neumann's and the Born interpretation as well. So you are in serious trouble if you don't have the positivity of the hybrid density. And then you have to propose something else. It can happen that you have a theory which yields an indefinite density, but then you have to propose a new interpretation for it instead of the classical probabilistic interpretation and instead of Born von Neumann statistical interpretation. So it's a la Bonheur if you have an equation which violates the positivity of the density matrix, but then you have to replace the common statistical interpretations by some new proposal.
So if do I understand it correctly that you're aiming to quantize gravity via the hybrid theory, right? Because maybe there's something, maybe there's a joint quantum theory where one sector behaves almost always semi-classically and reduces to GR. So that would be another way, right? If I start from a quantum theory which is fully quantum and never hybrid, then I have positivity for free if I prove unitarity.
Yes.
But then the difficulty is to show that effectively it reduces to the behavior that we know empirically. So standard model, which is quantum, and then GR, which is semi-classical. So that's then practically difficult, probably, because we have to understand the physics of such a larger theory. Or you're saying the other approach would be one where I have just the difficulty of showing the positivity, but I just start with what we know, what the empirical starting point is, yeah? Which is another way to go at the problem.
No, I mentioned two ways to go. One, when everything is quantized, and then of course you can introduce effective equations to describe the almost classical behavior of gravity when it is really almost classical. But you have a fully quantized theory valid at the first instances after the Big Bang, where we think that if gravity is quantized, it behaves quantum mechanically. So you cannot use an effective semi-classical equation right after the Big Bang. Okay, this is one way. Then your effective equation may, if it is a relatively good one, it preserves positivity, but it may have other difficulties. I mentioned causality in case of standard semi-classical gravity. But the other way is more challenging when you forget about quantized gravity and you are looking for, from scratch, you try to construct hybrid dynamics for the quantized matter and classical space-time in interaction. And then if you construct it, then you are obliged to preserve the positivity of the hybrid density. Because if you fail to guarantee the positivity, then you fail to apply standard statistical interpretation, and then you are in trouble.
Could I ask you about something else? Because I'm also wondering about, so I never had any chance to talk to people actually working on those problems. So my question is, what are the physical demands for such a quantization program or such a unification program? So for example, if I would manage to have such a hybrid consistent framework, then I want to use it for physics. But by definition, my framework will entail GR as it is. But we know that there's the maybe not issue, but the question of singularities in black holes, right? So what should I expect from achieving such a framework to make predictions on that quantum gravity problem in some way?
Since we do not know what such a hybrid structure would look like, we only have some general expectations, and one of them is that according to my present understanding and the understanding of many of my colleagues, the new feature is the loss of reversibility. So the dynamics becomes noisy or even dissipative, but above all, irreversible. Because as I said, my ultimate understanding is that you can unify classical and quantum dynamics at the compromise that the resulting theory is irreversible. So this is my only prediction about would-be hybrid theory of gravity and quantized matter.
I don't want to hijack the discussion, but could you maybe point me to some examples? Because I was trying to follow the talks, but I'm completely new to the subject. So I think that was something that people pointed out, that the stochasticity is popping up when you're trying to make the hybrids.
Yeah.
Could you name the simplest example? Maybe a qubit coupled to some heat bath or something like this, where I would see that suddenly I need this irreversible.
Yeah, I gave the simplest example in on my slides.
Yeah.
But there is an oral argument, verbal argument, which goes like this: if you couple a deterministic classical particle, say, to a single qubit, then the behavior of the particle will inherit the quantum uncertainties of the qubit. So therefore, the classical trajectory of the particle becomes uncertain as well. It becomes statistically smeared.
Yes, I follow that. So I couple to something noisy. The noise here is maybe quantum in its origin, but how do I get the irreversibility out of that?
If any noisy system is irreversible. Noise means that you don't have control part of the dynamics. So you can, if I give you the coordinates of such a system today, you cannot calculate them for yesterday.
Perhaps I can add another source. Absolutely true. Perhaps I can add another source that has to do a little bit with what I presented.
Yeah.
If one has that divergence of V term in the equation, and by the way, that exists in the absolutely quote unquote classical, not classical in the sense of classical mechanics, but classical in quantum mechanics, Fock, Curve-Dirac space equation. That term actually is there.
Really?
What one finds is that if the system is chaotic, there is actually irreversibility, or rather irreversibility in the sensitivity to initial conditions sense, in the sense that the Lyapunov exponent can be positive, and there is an effective unpredictability that shows up, and the continuous spectrum ports from the classical to the quantum world. So I just want to add that to the picture. And noise, of course, contributes to that, and then also perhaps this irreversibility from chaotic dynamics.
Yeah, it's interesting, but it is largely different from the noise source I mentioned, because a single two-level system, a single qubit, will make your particles trajectory uncertain.
Yeah, I completely. Yeah.
So it is a different source, but it's good to see that. I have a colleague who used to swear that uncertainties come, quantum uncertainties, and uncertainties in measurement process should come from classical chaos.
And just for the record, I'm actually not saying only that. I'm actually subscribing to the point of view that what you said is one source.
Yeah.
And in particular, maybe I can connect it. I did mention in the talk, however much time I had, that there is a certain resonance that can appear between the observation field and the underlying wave that determines whether we see anything or not. But that particular moment or aspect is uncertain. There is an uncertainty in the fact that the observation field and quote unquote particle are moving differently, and if they resonate, but when they resonate and how they resonate.
That's important. That's uncertain.
Yes, and that you can link that to models of Newton-Schrödinger type, where it can be derived from the idea that the metric is actually uncertain, that it's moving around. It's one remarkable thing is that one can literally derive some of those models from what I've said. If one takes the appropriate metric, then the interpretation is exactly that the observation field moves in a stochastic way, and it's precisely the same. Although I do know you had some objections to Karol Haas's model, or
it's just on the realization of the model, not on the philosophy.
I see. Okay, so it's consistent with the philosophy.
Yeah,
it's consistent with the philosophy. Yeah. Okay.
Yeah.
Okay. Any more thoughts? Or maybe we can close the meeting now and resume tomorrow.
Please organize the dinner.
Actually, I wish we could. I so much we could do that. Believe me.
Maybe another.
All right. Okay. Thank you very much.
Maybe another meeting once purge is over.
Thank you very much, everybody. And have a good one, and see you tomorrow. Bye.
It was very nice.
Thank you.
Thank you.